Hello everyone, I'm Essen, and in this presentation I will be talking about design and analysis of smart antennas beamforming technique for 5G communication. Right, so we will start with the usual three questions of what, why, and how in context of beamforming. So first one being the what. What exactly is beamforming architecture within 5G communication? So beamforming is basically a technique to focus a specific wireless signals towards a receiver rather than spreading it in all direction, as is the case in broadcasting that signal or choosing the isotropic antennas. As a result of this specific and directive signal, we get a much faster and more reliable communication, which wouldn't be possible without beamforming communication. This directive beamforming is produced using array antennas, which are also called smart antennas, which uses the concept of constructive and destructive interference of the signal in order to cancel the signal in the direction of signal not of interest, which is also called SNOI, and it basically makes a highly dense signal within the direction of the signal of interest, which is called the SOI. This constructive and destructive interference to cancel or produce a highly directive beam in a specific direction or to cancel it from other direction is also called spatial selectivity or filtering, which is basically to construct or remove specific beams within the space or and to steer it and angle it in specific direction. So the process is also called spatial selectivity or filtering as well. This is made possible using array antennas, which are at the prime focus of the beamforming technique, and this presentation would primarily be talking about that as well. These array antennas are also called smart antennas, which are further divided into phase array and adaptive array system mainly, and we will further explore these two broad categories later on in the presentation. Right. So next question is, why do we need beamforming architecture, or why do we need beamforming technique within 5G communication? So as we know that 5G communication is marked by devices that are extremely intensive, and they need extremely high reliable and low latency communication in order to um, make the highly mobile data applications to be made possible. Right. So what beamforming does in 5G communication is that it provides highly specific or directive signal to the receiver, as a result of which we can deliver high quality, which as a result of which we can receive high quality signal with a much improved spectral efficiency, which results in much lower consumption of the bandwidth as well. Apart from that, beamforming helps us achieve the low latency by extremely fast transfer of information, and it simultaneously this low latency transmission takes place using at extremely low bit error rate or per. This entire beamforming power consumption is pretty much similar to the isotropic propagation, and because instead of radiating in all direction, we are directing our beam in one particular direction, and there is no need of additional power as well. Apart from that, beamforming can also reduce the broadcasting in undesired direction, as a result of which we can get an improved SNR or SIR as well, and then the interference for the of the undesired signal for other devices reduces as well. So in short, the need for beamforming is to improve the communication system in terms of speed, efficiency, and reliability, and also to reduce the interference by improving the SNR of the system in order to meet the data hungry demands of the modern communication in our 5G applications. Right. After why, the question that comes is how is beamforming is achieved in 5G. So this presentation would primarily be dealing with the question of how, by discussing different higher domains of the 5G communication. So on the screen, you can see the high surface level block diagram of the flow of the presentation that we will be discussing. So this is smart antenna beamforming technique is for this presentation or for this case study is studied in 4 different domains. We already discussed the beamforming architecture in the question of what exactly is beamforming. Next, we would be discussing the smart antenna theory, which is basically at the core of the beam generation. So smart antennas are basically the hardware architecture which makes directive beam possible. Within a smart antenna, we will study the key elements which are present in the smart antennas. Then we will talk about the how these smart antennas are able to locate a particular object using the simplified propagation model. This one, and then we will talk about two different broad categories of smart antennas, namely uniform planar array or UPA and uniform linear array or ULA. And finally, we will talk about one of the smart antenna model structure with reference to one of the paper. Once we have established ground for smart antenna theory, we will then talk about the theoretical framework or the entire mathematics of the beamforming, in which we will primarily be looking at the weight generation or weight calculation for the beam using the DFT based code book or discrete Fourier transform algorithms. Then we will talk about the UPA beamforming or uniform planar array beamforming mathematical framework, followed by two major main kind of theoretical generation of the beamforming, namely adaptive single beam approach and multi beam approach in context of user demand. Once we have established ground for theoretical framework, then we'll talk about the array model for beamforming, in which we will extend on the smart antenna theory, and we will talk about the different kind of array system that are available within the beamforming, namely phase array, which is usually fixed, and the other one is the adaptive array system. Mind the typo here. So this will be adaptive array system, which basically changes its weights in the runtime. We will discuss both of these categories in detail later on in the slide. And finally, we will talk about the array weighting scheme in order to calculate the weights for different key elements of the array of the smart antennas using different schemes, namely binomial, Blackman, Gaussian, and all of these. And then we will, once we have concluded on that, then we will talk about the simulation within the context of beamforming. So for the simulation, I performed two simulation for this case study. The first one is the simple uh, demonstration of the beamforming, and the second one is in the context of hybrid beamforming. Right. So moving on with the smart antenna theory for beamforming. So the first one being the what are the key antenna elements, what are the parameters which are used to study the smart antenna itself. The first and the primary and most important one is the antenna gain itself. Antenna gain is basically defined as the ratio of the signal strength in a particular direction compared to the isotropic radiation, or if the signal was propagated in all directions. This antenna gain is extremely important because this is what we use in order to calculate the complex weight for the elements. When I say elements, I refer to the smart antenna elements, which are basically the specific sub devices of any antenna or of any smart antenna. So any antenna would be made up of multiple elements, which are called the array elements, and depending upon the number of array elements, it would be able to have a much more better control over the beam forming as well. So again, referring back to the slide, the antenna gain is used to determine the complex weights, which contains information for the phase as well as the amplitude. This antenna gain is measured in dBi, which is the decibel in decibel isotropic, and this has to be measured with reference to the in regard to with some reference, and for the most part on beamforming, this reference is taken, the zero reference is taken to be the isotropic radiation, which is radiating in all direction. Apart from antenna gain, another important element of the array or of the smart antenna is antenna pattern. Antenna pattern basically defines the entire beam generation with its main lobe as well as the side lobe. So the final output of the antenna or of the smart antenna in form of wave is called the antenna pattern. Antenna pattern have main lobes and side lobes, and for each lobe we have very important parameter which is called the half power beam width or HPBM. This defines how narrow or how wide the beam will be, and as a result of which this will define how far the beam would be able to propagate, or how many user would it be able to would it able to be served in a specific region. So HPBM is a parameter that we will be discussing throughout the slide, and also in the context of the simulation as well. After array pattern or the entire output of the beam pattern, we talk about element pattern. Element pattern, as I talked about previously, is the design of the array of the smart antenna system. So element pattern can be of different type. It can be either linear, it can be either planar, or it can be divided in a grid or so on. And these element patterns defines the entire orientation of the smart antennas, and are designed usually using the same third generation partnership program standards. right? After that, we have the simplified propagation model. For any smart antenna, in order to calculate the location or dislocation or the movement of any receiver, we had to have some sort of model. So there are many, sorry about that. So there are many different kind of models that can be used to locate the receiver, but this is one of the most simplified propagation model that can be used to calculate the to calculate the geographical location of any user. So for this simplified propagation model, we use a spherical coordinate system which has two most important parameters, namely theta and delta, which are the angular displacement out of the receiver in a spherical coordinate system. So the first three equations right here gives the actual location of the user in at the coordinate system of XYZ. So I won't be going into the details of these mathematical expression, but I will be only referring explaining them over in an abstract form in order to convey the idea. For details, I have written a detailed document that I can share it within the link of this video. So if you want to explore the details, you can refer to that link as well. Right. So once we have the location of XYZ, the small change in its location of the receiver can be found using these integrals right here, which tells us about a small change with respect to the theta as well as the delta. And we will be simply taking their integral. Right after using integration by part, we obtain the following three expression of dislocation x, dislocation y, and dislocation z. Sorry about these typos here. So these three expression gives us the dislocation of any object or the receiver when the receiver move from one particular area to the another within the spherical coordinate system. The receiver, the transmitter or the beamformer would be able to calculate that dislocation based on these three expression. Again, I won't be going into the details of these expression, but these expression in essence tells us about the location or the movement of the receiver or the target device or the user equipment. Right after the simplified propagation model, we have the smart antenna uniform linear array. So as I was talking about different element pattern previously in the previous slide, this one is the uniform linear array in which we have n elements which are linearly oriented together and are separated by the distance of d, and each of them has the weight vector of W1. Weight vector, it contains information for the phase and amplitude of the beam that each of these elements would produce, and together, after constructive interference of these waves by each of these elements, we would have an entire array pattern or the entire main lobe in addition with the side lobe as well. Right, so the combination of the complex weight will allow us to steer and angle the main lobe with reference to the bore side. Bore side is the direction of the beam which is produced when all of the weights are similar, or all of the weights have equal magnitude and equal direction. So if that is the case, then we would be receiving the beam or main beam within the bore side. But if we change the and weights complex weight in terms of their phase and amplitude, then we would be able to steer the signal direction as per our desired need. Right, extending on uniform linear array. So the entire array the entire array pattern that is generated using with main lobe and side lobe is given by this expression right here, which is the product of the array factor and element pattern. Element pattern we previously discussed, and array factor is the main component here. Array factor basically tells us about where to angle, what weights to select in order to angle or in order to steer the particular beam in particular direction. Right, so array factor will contains the entire information that we need in order to generate a complex weight for our antenna pattern. Right, so the expression for array factor is given by this. Array factor also depends upon two main parameters of theta and phi, which are the two main angles within the spherical coordinate system. And for each of the n element array element that we discussed previously, we will have different array weight vector given by Wn right here. So Wn is the weight vector and it is a complex weight vector. So it is expanded here as An plus Jbn. It contains complex part as well as the real part. Hence, it will have some magnitude and direction and phase associated with it. Secondly, we have this complex and a complex expression multiplied with given as e to the j k r n, where k is the wave vector given as Wn or the complex value weight. So k tells us the wave number in which is present for each of the element within the antenna. So this factor, this parameter k right here is something that we will discuss in detail when we'll talking about simulation as well. So for now, it can only be thought of as the wave number. Similarly, we have the Rn right here, which is the equivalent conversion of the spherical coordinate system to Cartesian coordinate system, and gives us the location of the receiver or the user equipment at Rn, Y, and Zn right here. Right. So once we have the array factor, we have simply the weights. In short, having array factor means having the complex weight for beam generation, and then and when this array factor is multiplied with the element pattern, which is either linear or in grid form, produces the entire array pattern, which is basically the main beam produced. Right. Apart from uniform linear array, we have the uniform planar array. And just like linear array, we can instead have a grid as well. Here we have a NH by NB grid, where we have H horizontal horizontal elements and V vertical elements, and they together form this entire grid right here. These are separated by each of these elements is separated by a distance of DH and DV in direction of horizontal and vertical. And similarly for these arrays or these grids form a structure which are referred to as sub-arrays. So sub-arrays might have weights that are dynamic or static as well. Some of the sub-arrays might change their weights in the runtime. Other might have constant weights as well. Right. So this is also something that we will discuss in details when we will be talking about the weight calculation or complex weight calculation for the array system. Right. So the orientation, size, and structure of the subarray, and depending on how many of the subarrays have a static or dynamic weight, will help us determine the coverage of the beam as well as the beam width as well. Beam width is the parameter that I was talking about earlier, HPBM, or half power beam width as well. Right. On the right, you can see the graphical representation of such a subarray, and we can also see here that different subarray weight can combine together in order to generate a specific signal in a particular direction as well. Right, so we will conclude the smart antennas on this one of the model structure. So this is in the context of one of the relevant paper that I found, in which a simulation for the smart antennas was performed in the software called HFSS, or high frequency simulation software. So for this particular antenna, the author used the following formula for the radius calculation of the antenna, of the round antenna. So it doesn't have to be round, but within the context of the paper, the author used the following geometry of the antenna with around 8 to 12 antenna elements as well. So for that purpose, he calculated, or he derived the following expression to calculate the radius of the antenna, in which we can see it depends upon the h, which is the height of the antenna, and rho as well, which is the constant depending upon the material used for the design of the antenna. And based on the simulation result that this author obtained, he was able to derive the path loss model as well, which he gave with using the expression FSL. So on the bottom, you can see the FSL is given by 4 pi square divided by lambda square, 4 pi r divided by lambda square, sorry. And the final path loss model that you obtained using the simulation software, or the um, empirical uh, empirical behavior that he obtained within the simulation, he was able to obtain the following path loss model for his smart antenna, which is given by 92.4, the constant, plus 20 log f plus 20 log r. So path loss would depend upon the frequency. For the simplified model, the path loss would depend upon the frequency as well as the radius. And on the right, you can also observe the simulation results as well, along with the current density for a smart antenna. So current density is essential to be studied in order to determine the direction as well as the gain of the antenna as well. Right. So after that, we will be talking about theoretical framework for the beamforming, in which we will be primarily looking at the mathematics that is involved behind the beamforming structure. Right. So in order to calculate a complex weights for each of the element within the antenna or the smart antenna, we usually use discrete Fourier transform, which is DFT based algorithm, in order to determine the weight vector for each of the antenna element. A weight vector is something that will contain the information of phase as well as the amplitude, and these weight vectors are then added together by superposition principle in order to give the entire weight vector system of the antenna of the entire smart antenna as well. So weight vector for different elements of the antenna can be added using superposition principle in order to get the entire weight vector of the whole system. A superposition principle is used because the net effect of this weight vector would be equivalent to summation of individual effect of the element of the antenna element as well. So this expression on the right shows us the weight vector for each of the antenna element. As you can see, it contains different code words or the weight vectors represented by m, and there are total of roughly 2n weight vectors for each of the element or for each of the antenna element. And these specific entity of this vector tells us about individual element gain and the phase that is associated with it. And by adding all of these together, we can obtain the entire weight vector of the system. And wn here represents the weight vector for nth element of the antenna. Right. So, and the need for having a two for having two n weight is primarily to meet the Nyquist criterion for the transmission. Right. So after that, we have the adaptive single beam approach within the mathematical framework, which tells us about the so in adaptive single beam approach, we have a single beam with side lobes that are not as relevant and are usually unwanted. So this single beam approach can either have a narrow beam, which will have a small high powered beam width, or HPBM, high powered HPBW with, and it will have a high gain and will be extremely directive. Narrow beams are essential when we have a user which are situated in far away or similar location, compared to wider beams which are ideal for usage where multiple users are located in a nearby similar region. Both narrow and wide beams have a single main lobe along with multiple side lobes. Apart from this approach, we also have multi-beam approach. In multi-beam approach, there are usually two or more main lobes along with the side lobes. These multi-beam can be produced using the using multiple different weight vectors for different directional main lobes, and then we average out these resulting weight for L selected weight vectors. On the bottom of the screen, we can also see the the geographical representation of the multi-beam at different phase angles. Each of them have the main lobe followed by multiple side lobes as well. Multi-beam approach is useful when we used to utilize the same antenna in order to serve multiple users in either nearby or far away regions. Right. Apart from that, we have the UPA or uniform planar array beamforming, which we talked about earlier. So it will include a grid of the element pattern, usually given by NH and NH by NV, NV times grid. So in order to calculate the entire weight vector for this uniform planar array, we again use the discrete Fourier transform algorithm, which take place differently to calculate the horizontal weight and differently for the vertical weight. So there will be two set of weight vectors. The first one would be for the for the vertical generation of the beam, and the second one would be for the horizontal generation of the beam. And these together can be used to find the entire weight vector of the system by taking the knocker products of the azimuth or horizontal code book with the zenith or vertical code book. So using the DFT for horizontal vertical, we can find an entire weight vector system for the entire grid, and which on the right can be seen serving a specific IoT device at the angle of theta and phi. Right. So next we will talk about the array model for beamforming. So this is an extension to the smart antenna as well, but this section would primarily be focusing on the different kind of the array system that we have for beamforming architecture. So for a phased array system, the normal phased array system will contain predefined weight patterns for specific directions. So it will be set of complex weight that are pre-calculated and would not be calculated during the runtime. And these only provide limited direction of the beam to be generated uh, in a specific direction. And say if the user is not present or the receiver is not present in any of those given directions, then this normal phase array system will stand invalid and would not be able to serve that user. In contrast to the normal phased array, we have the adaptive array system, or AAS, which will readjust the weights in real time, and it can theoretically produce infinite beam patterns in infinite directions, and hence is much more robust compared to normal phased array system. So this is essential in application which have a high mobility, or the where the user is continuously moving. So in that scenario, in that application, we have adaptive array system to be much more feasible. In an adaptive array system, we have the weights being calculated iteratively to meet a target SIR and the signal power as well. So weights are calculated iteratively in order to calculate the target SIR as well as the signal power, in order to reduce the power, in order to improve the power efficiency, and also reduce the interference. Weights calculation does not require complex hardware circuitry and can easily be calculated using the advanced software-based digital signal processor algorithms. On the right, you see the the graphical representation of the phase of the array system. As we can see, we have this main lobe with in a specific desired direction, along with some undesired side lobes, which are generated by the constructive interference of multiple antenna elements, and given by antenna 1, 2, all the way till 4. All of these which have different weights given by W1 all the way till W4. And they are added together by superposition principle. And these weights are calculated using DSP-based advanced algorithm, and can be added together using superposition principle in order to generate the main lobe in a specific direction. Right. After that, we have the array weighting scheme. In order to calculate those complex weight, we will have different kind of schemes, namely binomial, Blackman, Gaussian, Hamming, Kessler-Bessel, and Chebyshev. So these specific schemes are valid in different contexts. For example, depending upon the frequency of the transmission, depending upon the height of receiver and transmitter, depending upon the distance between the transmitter and receiver, and depending upon the type of region that we have, the geographical region, whether it is urban, suburban, rural, or densely urban area. Depending on all of these parameters, we would decide which array weighting scheme that we have to use. And each of the array weighting scheme would be more optimal and will be more beneficial to be used in that particular with their particular parameters compared to the others. These are some of the array weighting scheme. There are a couple of others as well, but these are some of the ones that I identified within the literature survey that I performed for this study. So for binomial array weighting scheme, there are no side lobes produced, but only main lobe, and weights can be found using Pascal's triangle. So again, I won't be going into the detail of the math. For that, you can refer to the detailed document that is attached within the link of this video. Next, we have the Blackman given by the following expression with the wave numbers given by the K. Then we have the Gaussian, which is due to the Gaussian distribution of the considered Gaussian distribution of the users, with again the wave number given by the K. Then we have the Hamming weights given by the following expression with some constant, and the wave numbers, and then we have the Kessler-Bessel expression, and finally the Chebyshev expression. So some of these expressions are empirical in nature, meaning they were calculated using data collection, and then determining or producing a model from that data. And others are more theoretical, meaning they were performed those expressions were performed mainly on basis of the theoretical analysis rather than the empirical data or anything. Right. So moving on, right. So I found one of the paper where some of these array weighting scheme was used in a particular area. I think it was dense urban or something in that context, and these different weighting scheme for use, and the results were discussed toward the end. So I thought it would be relevant to discuss the results in context of that paper within this case study. So as you can see, we have different algorithms, and associated to them are this different beam width, or SLL, which is the side lobe level, and the gain. So the study that was performed within the context of this paper found that Kessler-Bessel was the most optimal choice for the weight calculation, because it provides the small side lobe level, because we want to minimize the side lobe level, because entirely we want the main lobe to have the most power, and it has the most gain as well, and the beam width. But again, it should be noted that this study was performed in a particular geographical location and is in context of that alone. Right. Also, the same study also reported the results in terms of good port, STR, and PSNR for the 5G and 5G optimal. 5G was 5G optimal included the optimal beamforming, and 5G did not. So the results I thought were relevant to be discussed here as well. Since 5G optimal used optimal beamforming compared to the 5G, and it can be seen that STR, which is a successful transmission ratio, is greater for the 5G optimal, which is basically the ratio of the transmission data successful compared to the attempted ones. And similarly, the uplink and downlink output is also good, meaning the average bit exchange per transmission delay is good for the 5G optimal. And PSNR, or the peak signal to noise ratio, is also good for the 5G optimal. Or the ratio of the maximum signal quality of the transmission to noise is more robust for the 5G optimal. So in short, this slide basically tells us that the 5G optimal 5G in addition with the optimal beamforming would provide much more robust system in terms of good put SDR and SNR as well. Right. So this is where I will conclude the presentation, and I will move on towards the simulation. So I would not be running the simulation because I would be running the simulation, but not for prolonged period, because it might cause some lag to my system. So I already have shared some of the results within the slide, and will show you some later on as well. So the first simulation that I performed was to study the traditional beamforming, and in this simulation, um, I will discuss the code as well, not in detail though, but these are some of the most important parameters that were present in the code. So first one was the frequency of the wave of the propagating wave, given by, for this case it was 1 gigahertz or 1 exponent 9 hertz, as can be seen here. Then we have this free space speed given modeled by c, or the speed of light. Then we have the lambda right here, which is the wavelength of the wave that we are propagating, and the t is the time period. And then we have the omega, which is the angular frequency. And this parameter right here, k, given by 2 pi lambda, is something that I discussed previously as well. It was called the wave number. So k here, this parameter right here, 2 pi lambda, 2 pi over lambda, is basically given right here, right? This one right here. So in this array factor expression, this parameter k tells us the wave number, which tells us about the specific wave produced by the specific antenna element within our system. So this is the same parameter which is used in the simulation as well, right? Right here. Apart from these main important parameters that can be tuned, we have the other parameters that are essential for the simulation. So we have the number of samples per wavelength. In order to increase or decrease the speed of the simulation, we select the and we can either increase the ns or the number of samples. Similarly, we have the spatial discretization, which is basically the specific discrete samples present between each of the transition for the beam. Then we have other elements, other important parameters, such as number of times per period temporal discretization, and the error and the time vector that for which it needs to run. And then similarly, we have the angular discretization. So all of these parameters mostly deals with the simulation runtime behavior, and does not have much to do with the parameters of concern, which are mostly the first ones, including the frequency, lambda, omega, and k. And these last two parameters, theta and delta. Theta tells us about the orientation of the beamforming in the runtime, as to if we want the beamforming to change its phase angle or to rotate during the runtime, we can tune these parameters. So I will show you the results shortly as well. And finally, we have the generated domain given by the cosine and sine theta, which is basically the entire spherical or the circular domain that we are seeing. Right. So with these parameters, let's have a look on the right. Right. So for the first two cases, we can see that the relative phase difference is delta equals to 0, meaning they are in the direction of both side and are not angled or stayed anywhere else. Also, they are also the HPBM, or the high power beamwidth is given by this antenna separation parameter right here, d equals to lambda by 2 and d equals to lambda by 4. So as you can see, if the beam is narrow, meaning it has a low HPBW compared to then the propagation signal would be much more ideal for the far away users in that direction compared to nearby user, for which this case would be ideal, where the HPBW, or high power beam width, is much greater compared to this one. And for this case, it would be ideal for the nearby users compared to the far away users. So as you can see as well, with the main lobe being generated, there are side lobes as well, and depending upon the high power beam width or the antenna separation D or HPBW, we will have the number of side lobes decided by that. So this test case was repeated with different. So I then tuned this relative phase difference using delta all parameter right here and at the 45-degree angle, and the bottom two are the simulation result for that with the same antenna separation, but now the phase angle is 45-degree, meaning the direction of the beam is not changed. Right, so I will shortly show you the simulation as well and different test cases, but let me briefly discuss the other simulation that I performed for this test case, for this case study as well, which was the hybrid beamforming MATLAB simulation. So apart from the simple demonstration of beamforming, I also want to explore what exactly hybrid beamforming is, and I found one relevant simulation as well. So I will discuss that in as well. So within optimal beamforming, are usually using we are usually using the entirely analog system or digital beamforming system. So within analog system, we have single wave that are fed into the all the elements of the antenna, but they are differentiated from one another using the phase difference. So the wave is same, but they are separated by one another, or the elements are separated by one another using the phase shifters. So optimal beamforming usually does not, or sorry, analog beamforming does not require robust hardware because there is only single wave generation, and they are phase shifted in order to direct the beam in a particular direction. But the drawback of this analog beamforming is that we are only able to achieve one particular beam using one single antenna. Comparing that to digital beamforming, we use different waves which are fed into different antenna element, and different main lobes can be produced by digital beamforming. But the drawback here is the usage of more advanced hardware, because now we are not using same wave as we were using in the analogous case. So for digital beamforming, the complex hardware circuitry is required. So in order to create a more optimal solution between analog and digital beamforming, we have a type of beamforming which is called hybrid beamforming, which is basically the complex mixture of both the analog and the digital beamforming. So hybrid beamforming basically reduces the hardware cost, hardware complexity, hardware security as well, and at the same time is able to produce multiple mail lobes for multiple users with the same smart antenna. Right. So as you can see, this is optimal beamforming. This is something that we desire. Using either using completely digital beamforming or analog beamforming, and this is the hybrid beamforming. Hybrid beamforming, we can see the results are almost similar, and the main lobes that are generated are also in the same direction. But it should be noted that within the optimal beamforming here, the hardware circuitry is much more and the cost is much more, and overall complexity of the system is much greater than hybrid beamforming, where we have reduced the cost of the hardware because essentially we are reducing the number of generators as well, and we are also reducing the complex circuitry as well. So hybrid beamforming is, although is giving slightly different result, but it is much closer to optimal beamforming at much reduced complexity, at much reduced cost, and at almost the same efficiency and at the same um, directive provides the same directive beams as the optimal beamforming. And the result for both of these is discussed in this graph right here. So it can be seen that for hybrid beamforming is so NS1 and NS2 basically tells us about the data stream. NS1 for both the cases include one data stream, and NS2 includes two data streams. So as the data stream would include for the same antenna, or the spectral efficiency will also include, because we are able to serve more user using the same antenna, right? So hybrid is almost near, as you can be seen in the graph. Hybrid beamforming is almost near the optimal beamforming. And if we increase the data stream, then we are essentially increasing the spectral efficiency as well. Right. So this was it as far as the presentation was concerned. Now let us just quickly move towards the simulation. So this is the simulation for the demonstration of simple beamforming. These are the parameters that I already discussed. This was for the how much orientation or what angular displacement should be for the beam that is generated. These are the parameters that I discussed within the slide. Apart from that, I also wanted to quickly discuss this parameter right here. So in order to decide the HPBW or high power beam width, we can tune this parameter right here. The rest of the code simply deals with the generation of the model. So I would not be going into the details of it because I already have discussed the um, main parameters that are essential to our simulation. Now let me just quickly run this simulation and show you the output. Right, so it can be seen here that the phase difference, so I'm basically moving my beam in at the angle of 45 degree from 0 degree. And it can be seen that delta is increasing slightly, and the beam is basically shifted from its phase angle of 0 to all the way till 45 degree. Antenna separation is, if antenna separation is greater, then we have a narrow beam width which can be observed here with more side lobes compared to more small antenna separation, which will provide a wider beam width, as can be seen here, with lesser side lobes. Narrow beam width would be ideal to serve users which are far away compared to this wider beam right here, which is more ideal for the users nearby and in a region which is near to the transmitter. Right, so this was for the simulation, and there are some of the other test cases that I performed as well. I recorded the videos. I will simply show you that. Um, right, so this one was for when the beam is oriented from all the way from the phase angle of 0 degree to 360 degrees. So it basically serves all the users in the nearby region by rotating from phase angle of 0 degree to all the way to 360 degree, and it can be observed as the angle is being changed, or the phase angle is being changed with the same antenna separation. Then what we observe is change in the shape of the main lobe in addition with the number of the side lobes. And at some points, the main lobes, there are multiple main lobes as well that can be generated. Um, and the other times the side lobe will dominate compared to the main lobe. So this one was for the entire 360 orientation of the beam. So this was the second test case, and apart from that, so sorry, this was the first test case, and for the second test case, what I did was I oriented it from 0 degree to 45 degree, which we also demonstrated within the simulation with the antenna separation of the following. And for the third test case, that change that I made was within the HPPW or high power beam width. It can be observed the beam width is now much more greater for the first case, and is given by t equals to lambda by 8, which was previously lambda by 2. So now the beam is much more wider, and is only ideal for the users which are very nearby compared to the users which are far away. So these are some of the parameters, including antenna separation, high power beam width, phase angle, antenna gain, frequency, which would determine the direction of the beam, the number of side lobes, the number of main lobes, the angle, phase angle, and the orientation of the beam um, in beamforming architecture. So some of the other parameters, for example, the carrier frequency was not. I tried changing to carrier frequency, but it does not had any significant change within the simulation right here, because it was primarily not demonstrated through these visuals or the graphical representation on the screen. Right. So this was basically it as far as the presentation and the case study is concerned. So I've also written a very detailed document about the entire work um, performed within this case study, which would be attached within the link below. So if you have any question regarding the mathematics or the framework or the phase array systems of the antenna or the simulation itself, you can refer to that document that I'm attaching with this link, within the link with this video. Right, so that is it from my side. I hope you liked and enjoyed this case study presentation. And if you have any question, please feel free to email me at this email right here, or ask me directly. So that's it. Thank you, and Khuda Hafiz, and do take care.